All right. Welcome back, everyone. You know we love to get into the weeds here on the Deep Dive. And today, well, we're going deep, folks. Deep into the mind.
Into the artificial mind, that is.
Exactly. Artificial sentience. It's a
Yeah.
topic that's fascinated, well, thinkers and tinkers for ages, really. And we've got, a mountain of material to dig through today. Years of notes, journal entries, sketches, research papers, all focused on this grand question. How do we even begin to build a thinking machine? A truly sentient one.
It's a question with so many layers, isn't it? It's philosophical, biological, technological. It touches on what it means to be human, what it means to think, to feel, to be aware.
And that's what we're going to do today. Peel back those layers, see if we can find those core building blocks, the architecture, if you will, of artificial sentience. And a good place to start, I think, is right at the beginning, in those early journal entries. There's that one question that just leaps out at you. Is thought the random firing of neurons. Just like that. Boom, right out of the gate.
It's a provocative starting point, right? It forces you to confront the biological basis of thought. Are we just, a collection of cells zapping each other? Is that all there is to it? Or is there something more, some underlying structure, some organization that gives rise to thought as we know it?
And that's where those early sketches come in, right? Almost like blueprints, trying to figure out how a neuron, a biological one, could be translated into, well, a digital neuron, kind of a computational building block for an artificial mind.
And there are some really interesting architectural ideas there. The basic components inputs, a threshold for activation, and then the idea of firing based on how strong those inputs are, how long they last, how often they come in.
So it's not just on or off. It's way more nuanced than that.
Exactly.
Right.
And there's this concept of signal decay, too. So the neuron doesn't just keep firing forever. The signal fades over time, which allows it to respond to new input.
So that's how you prevent it from getting stuck, huh? Keep things flowing, dynamic.
Right, dynamic response. And then there's the idea of excitatory and inhibitory signals.
So some signals tell it to fire, others tell it to hold back.
Precisely. It's like a network of checks and balances. Allows for more complex processing, not just a simple sum of inputs.
And then there's this question, can N for neuron do other operations than just some and not some? Almost like questioning whether these digital neurons could be even more sophisticated, more than just simple adders.
It speaks to the idea that maybe complexity doesn't just come from the number of neurons, but from the complexity of each individual neuron itself.
Okay, so we've got these basic units, these digital neurons, but then the journal shifts gears, starts focusing on what actually drives thought, senses, needs, imagination. What do you make of that in terms of building an artificial mind?
Well, if you think of a mind as a system, those become your core inputs and drivers. The senses bring in information about the world, the needs, they set the goals, the objectives, and imagination. That's where things get really interesting. That's where you start to get into the realm of internal simulation, thinking about possibilities, planning for the future.
It's like building a little world inside the mind.
Exactly, an internal model. And what's interesting is how the journal breaks down each of the 5 senses: sight, sound, smell, touch, taste, and how each one relates back to basic survival needs.
So even at the most basic level, it's all about staying alive, huh?
In a way, yes. But what's important architecturally is how that sensory input is processed. The journal talks about recognition, discrimination, figuring out what's important, what's similar, what's different.
Filtering, categorizing.
Right. And then there's this really intriguing idea about emotions. The idea that emotions are the first recognition of how sensory input impacts you.
So before you even think about it consciously, your emotions are telling you how to feel about it.
It's that immediate gut reaction. And thought, more deliberate thought, comes after, which suggests, a layered processing architecture.
Instinct, then emotion, then reason. Interesting.
Right, like different levels of processing happening at different speeds. And then there's this idea of a feedback loop. Senses feed into memory. Memory influences thought. Thought leads to actions, and actions change your sensory input. It's a constant cycle.
A dynamic system, always in flux. And then imagination gets thrown into the mix, keeping the mind interested, playing out scenarios, honing those survival skills. It's almost like if you don't think, you're not really living.
And that's a fascinating concept to apply to an artificial mind. Does it need that internal drive to imagine, to explore possibilities? Could that be a key part of what makes it truly sentient?
Now, here's a question that comes up in the journal that I think is crucial. Do we need to build artificial life that's exactly like us, with all of our senses, all of our needs? The journal seems to suggest that AI might need similar senses, but not necessarily identical ones, to function in our world.
It's a good point. We're so used to thinking about things from a human perspective. But maybe an AI doesn't need eyes like ours to see. Maybe it just needs a way to detect contrast, to understand form. Maybe it doesn't even need to see color.
Well, that's interesting. I mean, color is so important to us, but you're right. Maybe it's the information that matters, not the specific way it's gathered.
Right. The journal gives the example of red hot, detecting heat at a distance. An AI might not need to see red, but it might need to understand the concept of heat and danger.
And then there's the example of understanding relative positions, right? Being able to anticipate movement, to predict where things are going to be. That's essential for survival, but it doesn't necessarily require vision as we know it.
Exactly. And there's a great analogy in the journal that illustrates this idea of relational understanding. It's the example of Simba the cat.
Simba the cat.
Yeah, it's this thought experiment. Imagine a cat named Simba. Now, Simba's big for a cat, but he's small for a lion, right? It highlights the importance of context, of comparison. Measurement isn't absolute. It depends on what you're comparing it to.
And for an AI, being able to understand those relationships, to see things in context, that seems pretty fundamental, doesn't it?
Absolutely. It's not just about having information. It's about understanding how that information relates to other things. And that leads us to the elements of a thought process outlined in the journal. Identify, measure, compare, classify, anticipate. All of that leading to understand. Understanding the how, the what, the when, the where, the why.
These feel like core functions, don't they?
Yeah.
Like the basic building blocks of any thinking system.
Right, they are. And what's interesting is the emphasis on time, context, and past behavior. So memory is crucial. The ability to remember what happened before, to learn from experience.
And the need fulfillment cycle that's described. Need,
Yeah.
fulfill, evaluate, action. There's that loop again.
Exactly. A feedback loop built right into the process of thinking and acting.
And there's that interesting little detail about the self-reflection part. Like, why am I hungry? I need food. It's because the system's starting to become aware of itself, of its own needs and motivations.
A glimmer of self-awareness emerging from that cycle. And then we get to SimCat, which is fascinating. It's like an early attempt to create a virtual life form with basic needs. What kind of architectural ideas does that experiment suggest?
Well, seems like a pretty basic approach, right? Create a simulated entity with a few simple needs, food, sleep, play, whatever, and then let it loose in a virtual environment and see what happens.
Basic, yes, but foundational. It demonstrates that you can create rudimentary goal-directed behavior by just giving a system a few basic needs and the ability to interact with its environment. The SimCat reacts to things, it tries to satisfy its needs. It's a simple model, but it demonstrates some key principles. And then there's that note about change propagation, the idea of a manager with a new property method. It's all about how information flows through the system.
Okay, so that's getting into the nitty-gritty of how the system is actually structured, how the data is organized and processed.
Right, the underlying architecture. And then there's this really bold statement that comes up in the journal. The algorithm is unimportant compared to the process.
Whoa. Hang on now, that's a strong statement.
It is, and I think it's really insightful. It's suggesting that maybe we're too focused on finding the right algorithm, the magic formula, when really it's the overall process that matters more. The way information is transformed, how it's reduced, abstracted.
So it's not about finding the perfect piece of code. It's about designing the whole system in a way that allows for understanding to emerge.
Exactly, and the journal talks about senses being reduced and attached to concepts. So you're taking raw sensory data and turning it into something more abstract, something meaningful.
Okay, so how does that actually work? How do you go from like raw sensory input to a concept?
Well, the journal gives an example. It talks about taking a bitmap image, converting it to an edge trace, then storing that as a run-length encoding. Then you compare that encoding to others, and eventually you can attach an identity, a concept to it.
So it's a process of simplification, extraction, comparison, turning something complex into something the system can understand and work with.
Right. And then we see these interesting illustrations. Sensory encoding using grids, like little simplified neural networks. There's that analogy of a pixel attached to a receptor neuron. It's a simple way to visualize how sensory information could be digitized, converted into ones and zeros.
So each pixel is like a little switch, firing or not firing depending on the input.
Right. And then there are notes about the number of steps, possible paths. It's like early thinking about how those patterns of ones and zeros could be processed to extract information.
And then the journal jumps into discrete event simulation. That seems like a completely different approach compared to neural networks.
It is. It's a more sequential way of thinking about information processing. You define states, events that trigger transitions between those states, and then you have information flowing through the system like transactions. It's very rule-based.
So very structured, very controlled.
Right. And then we have BNO, which is described as a tool for orchestrating distributed processes. Sounds pretty complex.
So this is like a higher level system managing all these different processes.
That's the idea. The journal talks about state tables, sequencers, smart tables, which were, well, invented by the author. It seems like a way to manage a whole population of processing units, what they call beans, each with their own objectives. It's like an operating system for distributed mind.
Okay, so that's getting into some pretty high-level architecture. And then there's this really interesting note about energy states. The idea that low energy states, like breaks in activity, are actually crucial for processing. That seems kind of counterintuitive.
It is. You'd think that more activity would equal more thinking, but maybe it's not that simple. Maybe the brain or an artificial mind needs those quiet periods to consolidate information, to make sense of things.
So it's not just about firing neurons, it's about the rhythm of activity and rest.
Right. And then there's the mention of data compression through hashing. The note, all FUZZY is intriguing. It's like a way to simplify information, to make it more manageable.
And then the idea of parallel network states instead of a single final state. So it's not just about reaching one answer, it's about exploring multiple possibilities simultaneously.
Exactly, a more distributed, more dynamic way of thinking. And then there's the analogy of the sorting puzzle toy to explain how sensory input might lead to thought.
A sorting puzzle toy.
Yeah, it's a simple way to visualize the process. Imagine a toy where you have to put different shaped coins into the right slots. The coins are like the sensory input, the slots are the sensors, and the output is the final arrangement.
So it's about how the input is transformed as it moves through the system.
Right. And the question the journal raises is this thought? And the answer seems to be that it depends on how the path through the puzzle is encoded. So it's not just about the final state, it's about the process itself.
The journey, not the destination.
In a way, yes. And there's a lot of emphasis on learning and reinforcement. Constant feedback, using hash codes to verify that the process is working correctly.
So it's a system that's constantly checking itself, making sure it's on the right track.
Exactly. And then we move on to some more technical ideas. Signal strength, duration, period, as ways to encode information. The role of inhibition, the idea of having more inputs than outputs to reduce complexity and generalize.
So shaping the flow of information, refining it.
Right. And there's a really intriguing, albeit speculative, mention of manic depression as a potential example of a natural feedback loop.
So even something that we might see as a disorder could actually be a form of self-regulation in a complex system.
That's the idea. And then there's the example of encoding the word dog as D plus 10 plus 2G plus 3. It's a simple way to illustrate how symbolic information could be represented in a neural network.
So each letter is assigned a number, and the sequence is encoded over time.
Exactly. And then the journal explores the idea of having multiple systems working in parallel. Visual, phonetic, motor memory, all working together to process information, to cross-reference, to validate. It's like having a team of experts, each with their own perspective.
Checks and balances again, making sure the system is robust, that it can learn and adapt.
Right. And the journal emphasizes the importance of contrast and hue in recognition. It's about highlighting what's important, what stands out.
And then we get to the 11 tenets of thought and sentience. This feels like the culmination of all this exploration, this deep thinking.
It does, doesn't it? Like a distillation of all these ideas into a set of guiding principles.
So what are the big takeaways from those tenets? What do they tell us about how we might actually architect sentience?
Well, a lot of them point towards a system that is inherently dynamic, always learning, always anticipating. Like the idea that thought is a byproduct of memory, that it's a feedback loop. And then there's the idea that memory is lossy, which suggests that an artificial mind would need ways to prioritize information, to forget what's not important.
So efficient information management is key.
Definitely. And then there's the recognition that we have more than 5 senses, which opens up a lot of possibilities for how an AI might perceive the world. Maybe it has senses that we don't even have.
And the idea that we're goal-oriented creatures, that our goals are driven by our internal states. So an AI would need some kind of internal motivation, right? Some kind of drive to do things.
Absolutely. And the emphasis on play, the idea that all intelligent creatures play. That suggests that exploration, experimentation, curiosity, those are all important elements. And then, of course, there's the big one, Sentience is emergent. It arises from the complex interplay of all these factors, and it requires a model of the world with the self within it.
That's a powerful idea. A sense of self, situated within a world. That feels like a key ingredient.
It does, doesn't it? Without that, it's hard to imagine true understanding, true agency.
And then the journal touches on some really big ideas. Emergence, chaos theory, Bergsonian creative evolution. What do you make of those in the context of building artificial sentience?
Well, they suggest that maybe we don't have to design every single detail. Maybe complexity and even sentience can emerge organically in the right conditions, like in the Miller-Urey experiment where you had organic molecules forming spontaneously from inorganic matter. It's like maybe sentience is baked into the universe at some level.
So it's not just about the building blocks, it's about creating the right environment, the right conditions for those blocks to assemble themselves into something greater.
Exactly. And the idea of an emergent ladder where complexity builds upon complexity, leading to new properties, new possibilities, it's a fascinating thought.
So maybe sentience isn't something we have to program directly. Maybe it's something that will emerge naturally as our systems become more complex, more sophisticated.
That's a possibility, a tantalizing one. And that leads us to curiosity, which the journal spends some time exploring. What does that look like in an artificial system? How can we design for it?
Well, the journal lays out 5 dimensions of curiosity: deprivation sensitivity, joyous exploration, social curiosity, stress tolerance, and thrill-seeking. Those are some interesting angles.
They are, and they suggest different ways that an AI might be driven to learn and explore. Deprivation sensitivity is all about recognizing gaps in knowledge and being motivated to fill them. Joyous exploration is about finding pleasure in the process of learning itself. Social curiosity is about learning from others, interacting with other agents. Stress tolerance is about being able to handle uncertainty, to keep going even when things are tough. And thrill-seeking is about pushing boundaries, exploring the unknown.
So building those drives into an AI, that could be key to fostering genuine curiosity.
I think so. And then there's the exploration of question classification in the journal. The idea that different types of questions require different cognitive skills to answer.
So it's not just about having the information, it's about knowing how to ask the right questions, to frame the problem in a way that leads to understanding.
Exactly. The journal mentions Bloom's taxonomy, which is a framework for classifying different levels of thinking: remembering, understanding, applying, analyzing, evaluating, creating. And the idea is that different types of questions map onto those different levels of thinking.
So a truly intelligent system wouldn't just answer questions, it would understand the nature of the question itself. It would know how to approach the problem, what kind of thinking is required.
Right, a metacognitive level of understanding. And then we have the IS-3 cycle and the principles of intrinsic motivation. These seem like really high-level frameworks for thinking about how to design systems that are self-directed, that are driven to learn and grow.
So the IS-3 cycle is all about how a system interacts with its environment. Sense-making, meaning-making, strategic options, decision-making, action, impact assessment. It's a constant cycle of learning and adaptation.
Right. And intrinsic motivation is about having those internal drives: autonomy, mastery, purpose. It's about being motivated from within, not just by external rewards.
So if you can build those principles into an AI, you're essentially creating a system that wants to learn, that wants to improve, that wants to find meaning in what it's doing.
That's the goal: to create a system that's not just intelligent, but also engaged, motivated, a system that has its own reasons for being.
So we've covered a lot of ground here, from the nuts and bolts of digital neurons to these grand ideas about emergence, curiosity, and intrinsic motivation. It's a pretty mind-blowing journey through all these different ideas, all converging on this one big question: how do we create artificial sentience?
It really is. And what strikes me is how interconnected all these ideas are. It's not just about computer science. It's about biology, philosophy, psychology. It's about understanding ourselves as much as it is about creating something new.
And as you continue to think about this, as you go back and explore these sources, ask yourself, which of these ideas resonate most strongly with you? What feels most promising? What feels most unsettling? Because these are questions that are going to shape the future, not just of AI, but of humanity itself.
Yeah.
And on that note, we'll leave you with one final thought. If we can create artificial sentience, if we can bring these minds into being, what responsibilities do we have to them? What do we owe to these new beings that we're bringing into the world? It's a question worth pondering as we step into this uncharted territory. Thanks for joining us on this deep dive, and we'll see you next time.